Hi, welcome to Algebra 2 Common Core. Today we're going to start looking at exponential modeling. Exponential modeling is such an important topic in Algebra 2 that we're going to be doing several lessons introducing you and then getting into much more complicated exponential modeling problems throughout this unit and the next unit. So let's start with a beginner problem in exercise number 1. Suppose that you are starting with $400 in a savings account, and this savings account receives 5% interest per year. Part A, how much will this savings account increase by over the course of the year? So remember that we're starting with our $400. Because we know that our savings account is receiving 5% interest, we're going to multiply our initial investment, 400, times 5%. But it's important to remember that we need to convert 5% over to a decimal. So 5% as a decimal should be 0.05. Remember that from your percents way back in middle school. So 400 times 0.05 tells us that our account will increase by $20 each year. In Part B, if we take our $400 that we originally have, our initial investment, and we add on that amount of interest for the first year, we see that we now have $420 in our account. Now, if I wanted to know what I would have multiplied by in order to get that total amount after 1 year, I could write out what steps we really took in that evaluation. We had our 400, but then we added on 400 times 0.05. Now if we look at another way to write that calculation, I see that there's a 400 in both parts of this sum. So I can go back to beginning algebra and say, let's factor out that 400. And if I do that, 400 would be multiplied by 1 plus 0.05. So all I'm doing there is factoring a 400 out of this term and out of this term, and this is what's left over. So another way of writing this, 400 times 1.05. If you do that calculation on your calculator, you'll notice that yes, you do get that final answer of $420. So that becomes the clue as to how I'm going to start these exponential modeling problems. I'm going to say if I know my interest rate was 5%, then the multiplier has to be 1 plus whatever that rate was. Now I can figure out how much interest I have after any number of years by changing how many times I multiply by 1.05. So my equation becomes y is equal to that initial investment of 400 multiplied by 1.05, and that's going to be raised to the x power, where x is going to stand for how many years, or how many times I multiplied by 1.05. So in the first part of this example D, it says, let's find out how much money I have in the account after 2 years. So that is just going to be y is equal to 400 multiplied by 1.05 to the second power. That really means that I've taken my original answer of $420 and multiplied by an extra 1.05 to get 2 years now. So the answer now turns out to be $441. This one works out to be an even amount of dollars, so I'll just put 0.00 because I have money. How about 10 years? Y is equal to $400 was my initial investment, but then I need to multiply by 1.05 10 times. So that's why 10 is my exponent. When I do this calculation on my calculator, I'm getting $651 And I'm going to round this answer to 2 decimal places, 56 cents. So I see that the equation that I'm really using here is, they want me to write it as S of t in function notation. So S is going to be the amount in my savings account after t number of years. So I'm starting with my $400 and I'm multiplying by 1.05 raised to the t, where t stands for the number of years the money is in the account. This makes sense that my savings account is going to grow because I see that my multiplier, my normal b value in my exponential equation, is a number that's bigger than 1. So that tells me that this is an exponential growth problem. Now it says, using a table on your calculator, determine to the nearest year how long it will take for the initial investment of $400 to double. So in my calculator, I'm going to type in y1, so in my y1 key, put this function 400 times 1.05 raised to the x as my exponent, because that's what my calculator understands. Now I'm going to make my table of values, and I'm going to make my table count by years, so 1, 2, 3, counting by 1 years. And I want to know, when does this answer come to a value of 800, because I want to double my investment. So 400 doubled is equal to 800. Now take a second and look through your calculator table and see which year comes closest to $800. I got that it's going to take 14 years to double my investment. So check that on your calculator. You definitely need your calculator for today's lesson. So in the box where it says exponential growth in your notes, let's summarize the information that we have so far about exponential growth application problems. I'm going to use the variable r to stand for the fixed rate of increase. Now I'm talking about a fixed rate because I want to know how much my investment is changing each year. So I'm going to assume that R, that rate, stays the same each year. If it's given to me as a percent, I want to make sure that I convert it over to decimal form. The other information that I have to be given, sometimes we call the initial investment the principal. So we're going to use the letter P to stand for principal. Now don't get confused, because sometimes P is used for other things like population. But P, we're going to say, is our initial value, our initial amount. Whether it's people or money. And then in our equation, we're going to use T to stand for time. Usually the time stands for years, but we're going to see in the next lesson that our time can be any quantity. It can be months, it can be days, but for this lesson we're going to say T is time, usually in terms of years. So the equation that we have for exponential growth, A, I'm going to call amount, is equal to the principal or beginning amount times 1 plus r raised to the t. So this is an exponential growth equation where we know the rate of growth, we know the amount of time, and we know the initial amount. So let's try exercise number 2 using this equation. Which of the following gives the savings S in an account if $250 was invested at an interest rate of 3% per year? So for this one, we're going to say our S, our savings account, is equal to our initial investment, $250, multiplied by 1 plus the rate of interest each year. So we see that that's 3%. So convert that over to a decimal. So 1 plus 0.03 and I'm going to call the t time. So therefore I see that this equation is s is equal to 250 times 1.03 raised to the t. This is just choice number 3. So take a look at that and make sure that that equation makes sense to you. Let's try the practice problem at the bottom of page 15. We've got the population of Smithville in 2010 was estimated to be 35,000 people, with an annual rate of increase of 2.4%. Now right away I'm going to convert that 2.4% over to a decimal. So remember that to convert to a decimal, I'm going to move my decimal point 2 places to the left. So that's going to become 0.024 as a decimal. Remember, that's the same thing as dividing by 100. So what is the growth rate of Smithville? Well, our growth rate is just going to be our initial amount 1 plus our R value. So 1 plus 0.024. So that tells me that my growth rate is 1.024. Now, since this value is greater than 1, that tells me that I have exponential growth. So for an equation to represent the population, now don't get confused, we're calling P population now, so that's going to be on the left side of my equation. Population is equal to, in this case, 35,000 was how many people I began with in Smithville in 2010. But then I'm going to multiply by my growth rate, 1.024. And t is going to be my time in years, so that's going to be the exponent on 1.024. So if I want to use this equation to estimate the population in 2016, remember that my beginning year for this problem was 2010. So that tells me that 2016 just means that the amount of time that has passed by is 6 years. So I'm going to use t equals 6. So my population will be 35,000 multiplied by 1.024 to the 6th power. So when I put that in my calculator, remember that I have people, so I can't have a decimal answer. So go to the nearest whole number. 40,352 people will be living in Smithville in 2016. Now on page 16 in your notes, we're going to see how this equation is going to work with exponential decay application problems. So for exponential decay, using the same variables that we had on the last box, put our new equation in the box. A is still my amount that I'm ending up with. P is still my initial amount that I'm starting with. But this time, instead of adding 1 plus R, I'm going to subtract. So 1 minus R to the t. Now, when I go ahead and do that, remember that R is a rate and it's a decimal value. So when I take 1 and I subtract a rate that's a decimal value, what happens is that I end up with a base that's between 0 and 1. So that's what tells me that I actually have exponential decay. Now let's look at exercise number 3 so that we can see how this multiplier works when it's exponential decay. Exercise 3 says, let's state the multiplier, or the base, that I would need to multiply by in order to decrease a quantity by the given percent. So this time we're given that the rate is equal to 10%. So because I'm decreasing, because I'm doing exponential decay, my multiplier is going to be 1 minus, convert 10% over to a decimal, so that would be 0.10. Now let's go ahead and do that subtraction, 1 minus 0.10, and I see that my multiplier turns out to be 0.90. Yes, that is a value that's between 0 and 1, so of course that's going to show exponential decay. Let's try 2%. So this time we're going to say 1 minus 2% as a decimal is 0.02. So when I do that subtraction, my multiplier is going to be 0.98. Again, it's a decimal that has a value between 0 and 1, so that tells me that I've got exponential decay. For part C, 1 minus 25% would be 1 minus 0.25. That's going to give me the decimal 0.75. And yes, again, that's a decimal that's between 0 and 1, so this would be an exponential decay. Now, don't get confused when I've got a decimal within a percent. This decimal, so 0.5%, when I convert that over to a decimal, that's going to be 0.005. Again, remember the rule of thumb is just take your decimal point, move it 2 places to the left. So I'm going to have 1 minus 0.005, and that's going to give me as a multiplier 0.995. And while that's kind of close to 1, it's still below 1, so all of these have shown exponential decay. This was just practice in writing the base, the part of my equation that goes inside the parentheses when I'm doing a subtraction. So for exercise number 4, let's look at the population of a town that is decreasing by 4% per year. We see that the initial amount of people, 12,500, and we want to know what's the projected population in 10 years. So we want to write the exponential model that represents this. So we're going to say the amount of people will be equal to the original population, 12,500. But because I am decreasing population, this is exponential decay, so I want to say 1 minus 4%, so 1 minus 0.04 raised to the t power. So in this case, we're going to get that A is equal to 12,500 people multiplied by, my subtraction is going to give me 0.96, and I want to look at 10 years, so I'll raise it to the 10th power. When I put this into my calculator, I see that the number of people that I'm going to end up with, 8,310. Now, right away you should recognize that the number of people has gone down. I had started with 12,500 residents, but because my population was decreasing, I have a number that's smaller than 12,500 after 10 years. And again, remember that base being between 0 and 1 is telling me that this is an exponential decay problem. This is choice number 4 in our multiple choice answer. Let's finish today with exercise number 5. We're talking about stock prices, and the first company is called Wind Power Inc., and its stock price is increasing at a rate of 4% per week. Now you'll notice that this time our time is in terms of week. We're not going to change anything that we do, it's just that our T will be weeks instead of years. Its initial value is $20,000 per share. So I'd like to write the equation for Wind Power Inc. My value of Wind Power Inc. is going to be equal to the initial amount, 20, multiplied by, because my rate is increasing at 4% per year, I'm going to say 1 gets added to 0.04, so 1.04, to the t, where t stands for the number of weeks. For the second equation, this time it's called Gerbil Energy, and it's crashing. It's losing value at a rate of 11% per week. If its initial value is 120 per share, then we want to know how many weeks will it take for the two stock prices to be the same. So let's write the equation for Gerbil Energy also. Gerbil Energy is starting at $120, but because its rate is decreasing, we're going to say 1 minus 11%, so 11% gives me 0.11 to the t. Now I'm going to simplify that equation by doing the subtraction. So gerbil energy's equation will be 120 multiplied by 0.89 raised to the t. Now, hopefully you are recognizing that because 1.04 is above 1, wind power is an exponential growth problem. And because gerbil energy has a base that's less than 1, that tells us that gerbil energy is exponential decay. We'd like to know when these two have the same value. So we want to make a graph. I'm going to use my calculator to get some table of values for this. So I'm going to start you off, but then have you look at your calculator to get some values. So let's put T as our number of weeks in the first column. So let's start with 0 weeks, 1 week, 2 weeks. And you're probably going to have to scroll through your calculator to see where they're going to be close to equal to each other. W is going to stand for Wind Power Inc., and G will stand for gerbil energy. Now what I'd like you to do is go ahead and enter these two equations in your graphing calculator, fill in your table of values, and then we'll come back and look at our table and then do a graph. Welcome back. Look at your table of values and see if your table has the same values as mine. If it doesn't, please go back and check your calculator to be sure that you've entered the correct equation for wind power and for gerbil energy. Now what I'd like to do is set up a graph. Now I'm going to make my graph on the x-axis, on the horizontal axis, represent time, and on the vertical axis, that's going to be our price per share, the stock price. So I know that wind power started at 20 but got bigger. Gerbil energy started at 120 and got smaller. So on my price axis, I'm going to count by 20s on the vertical axis, but I have to make sure that I'm getting up to 120 because I have to have that much. Actually, I guess I'm counting by tens for each little increment, but I'm just marking every other one so that I'm up to 120. Along the horizontal axis, I see that in my table of values, wind power is getting bigger, but pretty gradually. Gerbil energy is getting smaller a little bit quicker because its rate of decay is 11%, which is a pretty big number. So along my horizontal axis, I'm going to mark every 5, and see if I can find out where the two cross each other. Now again, on your graphing calculator, what you're going to want to do is adjust your window. So when you change your window, you're going to hit the second key on the top row on your calculator. And let's make your window in the horizontal direction go from 0 to 20, counting by ones. The y's, let's make our y min be 0, our y max be 120, and let's count by tens. Go ahead and do that on your calculator, press graph, and then graph the two functions. We'll come back in a minute to talk about finding the point of intersection. Let's take a look at our graph, and please convert your graph, draw it on your axes in your notes, but also look at it on your graphing calculator. I see that the gerbil energy line and the wind power line do cross each other. I think I've labeled them incorrectly. Let me go back and fix that. Oh no. Okay, now I've corrected it. The blue line is the Wind Power Inc. and the red line is the gerbil energy. Now I can see that these two lines definitely cross right about here on my graph. Let's go to our graphing calculator, and on the calculator I'm going to press second trace, and I'm going to choose the option that says intersect. Now it gives me first equation, so I'm going to go to my blue line and I'm going to move the cursor over to close to that point of intersection and press enter. Then it says second equation, but I'm already at the point of intersection, so I press enter again. Then it says guess, so I'm going to press enter a third time. And what I see on my screen is that the point of intersection is 11.5, 31.4. So that tells me that it takes 11.5, or I'm going to say about 12 weeks in order for the two prices to match. So we've looked at this exponential problem using our graphing calculator, but it was important that we could write the equations first using exponential growth and exponential decay. Please familiarize yourself with the basic equations for exponential growth and exponential decay because we're going to be working on some application problems together in class. Have a great night, and we'll see you next time.